Okay, so last week we learned about empirical and molecular formulas. So if you were not here on Friday, you should have copied this note down. At least half of it we did on Friday. And so it says here that the empirical formula is the lowest whole number ratio of elements in a compound. So it shows the relationship for each element in a molecule. Whereas a molecular formula will show you the total number of atoms in a specific compound. So for example, the molecular formula for acetylene is C2H2, and the molecular formula for benzene is C6H6. So a lot of the formulas that we've been looking at are molecular formulas of our compounds. For example, sodium chloride. For every one sodium atom, there's one chlorine atom in sodium chloride. However, acetylene and benzene have the same empirical formula. So we can reduce the ratio for acetylene from C2H2 into CH by dividing all of the subscripts by 2. Same thing for benzene. We can reduce these values, C6H6, divide by 6 for the subscripts, and that will give us CH. So acetylene and benzene have the same empirical formula. So we also copied down this table here. If you have not already, please do so. And it says that different compounds can have the same empirical formula. However, molecular formulas can be different. Again, a lot of the compounds that we've been looking at have the same empirical and molecular formula, meaning we cannot reduce these ratios any lower. So for ammonia, 1 nitrogen exists in ammonia, and there are 3 hydrogen atoms. For water, its empirical formula is for every 2 hydrogens, there is 1 oxygen. So these compounds have the same empirical and molecular formulas. So the next part of the lesson, we look at steps to finding empirical formula. So this is a poem or a memory aid on the steps on how to solve mathematically the empirical formula. So the first step is we go from percent. If we're given percent composition, which was the last lesson we did before this lesson, if we're given percent composition, we convert those percentages into mass in grams. So percent to mass to moles, divide by small, and then multiply till whole. So I'll explain what each one of these means. And this is a flowchart on how the steps on how to solve for the empirical formula of any compound if we are given, again, the percent composition. And I'll explain this chart when we do our first example problem. So the first example says find the empirical formula of a compound with a percent composition of 83.1%. So change this value, it's not correct in your workbook. 83.1% sodium, and the remainder is nitrogen. So again, with percent composition, we are given that the mass percent of sodium is 83.1%, and the rest is nitrogen. So we can actually just solve for the mass percent of nitrogen by doing 100% minus 83.1%, which is 16.9% of nitrogen. So the first thing we do with a problem that asks us to find the empirical formula of a compound is convert from percent to mass. So the first part here, it says percent to mass. So the first thing we do is the easiest thing to do, assume 100 grams. So when we assume 100 grams, we can easily convert our percentages into grams. So for sodium, the mass percent is 83.1%, meaning in 100 grams of whatever this compound is, there is 83.1 grams of mass that is due to sodium. For nitrogen, the mass percent is 16.9%. In a 100 gram sample, 16.9 grams is due to the nitrogen in that compound. So we've assumed percent, or we've converted percent to mass. The next thing we do, if we take a look at our steps, convert mass to moles. So the second step is mass to moles. So I have my sodium and my nitrogen in mass, and I can convert mass to moles by doing mass divided by molar mass. So for example, for sodium, to get my moles of sodium, I'm going to take the mass, 83.1 grams, and divide it by the molar mass. So you can get this value in your periodic table. Sodium has a molar mass of 22.99 grams per mole. Your grams will cancel out, and this leaves me with 3.6146150 moles of sodium. Okay, so hopefully you got that value, 3.6146150 moles of sodium. Same thing for my nitrogen. So I'm going to take the mass of nitrogen, 16.9 grams, divided by the molar mass, which is 14.01 grams per mole. My grams will cancel out, and this gives me 1.206281 moles of nitrogen. So now that I have the total amount of each element in moles, the next step is to divide by small, or divide by the smallest number. Divide by small. So taking a look at the mole values of these two elements that make up my compound, I'm going to divide whichever mole number is the smallest. So in this case, it is nitrogen, so 1.206281. You're going to divide both mole values by the smallest mole calculation that you just did. So in this case, I'm dividing both of my mole amounts by the smallest value, which is 1.206281. And this, for nitrogen, will become 1. And for sodium's mole amount, 3.614 divided by 1.206, that gives me about 2.996. And we can round this to 3. Okay? So when you divide by small and you end up with a really a decimal number that is close, super close to a whole number, for example, 2.98, or if it was 2.95, or even 3.002, when you divide by small, you can, we are supposed to round to the nearest whole number. So what this is telling me is my empirical formula is that there are 3 sodiums for every 1 nitrogen. And this is going to be your final answer. So your final statement will say, therefore, the empirical formula for this sample is Na3N. So remember, when you're writing your chemical formulas, your metal always goes first and then your non-metal. In this case, it's sodium, and the non-metal is nitrogen. And this makes sense because if you think about the way that we cross multiply or crisscross when we're creating formulas, sodium has a 1+ charge and nitrogen has a 3- charge. So when we crisscross it, we end up with Na3N. So this is sodium nitride, and the empirical formula is Na3N. Okay, so I'll do the second example. You can pause the video, try it out on your own before, or you can follow along. So example 2 says, determine the empirical formula of a compound that contains 69.9% iron and 30.1% oxygen by mass. So again, the first thing we do is we convert our percent to mass. So in this case, iron will have 69.9 grams in a 100-gram sample of whatever compound this is, For oxygen, it is 30.1 grams by mass. The next thing we do is we go from mass to moles. So for iron, 69.9 grams, or we do our mass divided by molar mass. In this case, 69.9 grams divided by its molar mass, which is 55.85 grams per mole. My grams will cancel out, and this gives me a value of 1.251566 moles of iron. Same thing for oxygen. Convert the mass into its mole amount. So we take 30.1 grams divided by molar mass, 16 grams per mole. Grams will cancel out. And this gives me 1.88125 moles of oxygen. Third step, divide by small. So the smallest mole amount in this case is iron. So here I'm trying to figure out what the lowest ratio is. So that's why I'm dividing by small. So when I divide my iron by itself, obviously we are going to get 1. And then for oxygen, oxygen is 1.5. So when you divide by small, the mole amounts will cancel out. So these are just ratios here. Or it's saying for every 1 iron, there is 1.5 oxygens. So this is where that chart comes in. So notice how oxygen is 1.5. We can't round up or down because it's right in the middle of, or it's not close enough to a whole number value. So when we take a look at the fourth step, multiply till whole, if you have a decimal or a fraction that ends in 0.25 for your third step, you will multiply by 4 to get to the nearest whole number. If you have, for example, the question we're looking at ends in a 0.5 decimal. So we multiply by 2, we multiply all of our values, iron and oxygen, by 2 to get to the nearest whole number. So in this case, iron, so I'm going to put it over here, multiply till whole. For iron, it was 1. We multiplied by 2. And this gives me 2 irons. Same thing for oxygen. The 1.5 I got by dividing by small here. And because it is not close to any whole value or whole number, to get to the next or the nearest whole number, I have to multiply by 2. And this will give me 3. So what this is saying is for every 2 irons, there are 3 oxygen atoms in my empirical formula of iron oxide. So the way you would write that is Fe2O3. So this is the empirical formula. So again, whenever you have whenever you've multiplied or divided by small, in this case over here, we got 1.2515 divided by itself, which is 1. But when you do that for oxygen, we ended up with a number that is not close to any whole number. So we multiply by it till whole. So to get to the nearest whole number from 1.5, we had to multiply by 2 to get to 3. And we have to do that for iron as well. So this, again, it's telling me for every 2 iron atoms, there are 3 oxygen atoms. Okay, so I'm going to let you do the third example on your own, and I will post the answer for this. It's on OneNote already, so make sure you understand how to find the empirical formula using the 4 steps. So the 4 steps being percent to mass, convert mass to moles, divide by smallest mole number, and then multiply till whole. The chart here I will always give to you when you are finding what whole number to multiply by when you're given a decimal or a fraction. So for homework, I want you to practice solving for empirical formulas. There are just 5 questions, and yeah, that's it.